overview or the chair and discuss one of the research efforts at CIMMYT on wheat improvement, that is mobilization of the useful genetic diversity from the gene bank into the breeding pipeline through pre-breeding efforts. So I would like to thank to the Mexican government for the financial support and many colleagues, not only from CIMMYT and ECARDA, but from national partners such as Mexico, India, Pakistan and Iran, who has contributed the work which I am going to present in a few minutes. So as we all aware that green revolution has contributed significantly to providing global food security from last 3 decades or so. However, upcoming new challenges such as climate and growing demand for healthier food, genetic improvement of cereal or staple food crops such as wheat is very critical, and the next generation wheat varieties are expected to be more tolerant to various biotic and abiotic stresses, high yielding and also nutrient states. So these here, some of these land races are well known to are the sources for resistance to various biotic and abiotic stresses, and these sources or the sources of resistance for biotic and abiotic stresses need to mobilize into the pre-breeding pipeline successfully in order to address some of the issues which we are expected or the challenges going to for wheat production in the coming years. So it is not that we have not used these land races or wild relative before, but the way in the committed project with Mexican government, the scale and the systematic characterization and mobilizing gene bank diversity, as you have seen, CIMMYT and ECARDA has contributed significantly by providing the improved germplasm to the national programs and increase the productivity globally of wheat productivity globally. But if you look on other way, from last 20 or 30 year data, in most of the cereals is around 1% gain per year. In wheat it's 0.9%. So there is some things which we need to change or think how we can increase it. So if we look at the need for in 2050, the increase is required is by 2.4% per year. So to get that kind of increase, there are therefore different approaches and technologies and methodology are using by different institutions or international levels. A lot of initiatives are going on, and the one we are trying to do is synergizing the genetic resources with the genomic and harnessing the gene bank potentials with the focus on drought and heat. That is our target. But our mission as a CIMMYT is to deliver the product. In this project, we want to fill the gap of the gene bank and the breeders. So we bring the material in reasonable genetic background so that breeder can utilize easily, don't need to move a lot of drags. As you have heard other colleagues, Julie and others, they have mobilized a lot of the material from the tertiary gene pool, which have a lot of potential in the long run to mobilize. But I'm going to tell in a minute, the way we are thinking in this. So the first question we are trying to address, that we have 150,000 accessions in our gene bank. The first question for us is, which are the accessions we will use to mobilize in our pre-breeding program? So to do that, so we have the land races, synthetics and the wild relatives. As I mentioned, that our mission is to deliver to our breeders and then to the farmers. So we decided that land races or synthetics are the most short-term and mid-term impact which we can provide to our farmers. And I think the wild relatives are very important, but they are long-term investment, and we need to keep continue. And we have Masa Hero in our team at CIMMYT who is also carrying out some of those work. But when we come to the land races, then another issue has come to us. We have more than 30,000 land races in our collections. So as the project is funded by Mexican government, so we decided, okay, let us take one set of Mexican land races Then even the Mexican land races, we take 8,000 Mexican land races from the gene bank. And this slide gives us the idea, the integration of the technologies, expertise, and go from gene bank to the breeding programs. So the phenotype has been generated heat and drought and quality by Matthews, Carlos is here, and then we have the DART-seq data of all those 8,000 lines. Then we have a very nice biometrician and statistician team who helped to develop an algorithm and made a nice core set using data matrix of 75% genotypic and 25% phenotypic variation. And out we have these red dots are the assassins which are used in the core set, and about 90% of the rare allele is captured in these core set of 1,000 out of 8,000. They are representing very well, and this core set is freely available, and it's already distributed to large number of the scientists across the globe. They are using and finding these are very useful for different traits. Then go to the identification of the donor from these and mobilizing into the pre-breeding program. But as I already mentioned that our focus is drought and heat. So if we start looking the donors from today, it will take another 2 years to find reasonable donor for such complex trait, drought and heat. So then we have to look how to move forward. So although we are simultaneously doing the core set evaluation for drought and heat, but we at the same time start the pre-breeding process. These are the pre-breeding population exotics and elites which we have selected. We have the material from CIMMYT, land races are there, primary synthetics and historical breeding lines, and we took the best lines from Ravi's program, 25 lines, which have a good package of adaptability, diseases and everything. That is the heart of our, or the foundation of our pre-breeding germplasm. Then we have obtained the Acarda set, which are known to be tolerant to drought and heat, and figs, which are from different countries, Iran, Iraq, Afghanistan and Pakistan. So similarly, we have some collection from Australia, which have been tested under drought and heat. So we, based on those information, we thought this is a relatively better bet to move some of the drought and heat tolerant into our elite germplasm. So with this, then we have the germplasm, and we have to use the strategy here. We are using the strategy exotic 1 cross with elite and get the F1. F1 is back cross with the elite 2 and TC1 F1. So that way we have around 75% of our blood from our best elite lines. So that is the strength of our pre-breeding germplasm. Then 25% of the exotics, which we are expected to be through going through the selection in the drought and heat. So we will tap up in our elite lines. So then the second cross, we exotic 2 cross with the elite 2, which is used in the first population. So that way these crosses are linked. In the third cross, we will link with the elite 3, exotic 3 cross with the elite 3, and so forth. So that way we make a connective, that's why it's called linked top cross populations. So we have the panels of the population, we are linked with each other. That will give a maybe different option to the biometrician and statistician and lot of other scientists to figure out what are the interaction of the exotic allele into different elite background and so on and so forth. So that those are the population we have. This is the strategy we have used. I think the another important thing in the CIMMYT we have a beauty is that we have a lot of infrastructures. We can handle the large germplasm sets, as well as we have the lot of expertise in a group, in the team, so that we can make the selection and move forward. Here in the pre-breeding strategy, what with the exotic cross with the elite, this is the first breeding cycle I am going to explain. Then we got, we have initiated first breeding cycle in 2012, around 200 plus crosses. So for each cross or each population, we have 2,000 F2s. So we have started segregating population with around 400,000 F2 individuals. That is our initial breeding population. The way we are doing is pre-breeding, then we do the selection for drought and heat at Obregon, and then we do the shuttle in Tluk and Baltan, where we have the opportunity to reject the plants based on their agronomy or the susceptibility to diseases. So that way we move the plant up to F5. In F5 we select the individual good looking best plants. Out of those 400,000 we have selected in first breeding cycle, around 8,000 F5 plants. Those F5 plants again we planted at Elbathon and looked their agronomic performance and disease. Then we learned that it's better to reject maximum which are susceptible or not good in good. So around 1500 plants have been selected in the first breeding cycles, and we have the data for them for a preliminary yield trial, which is about 2 meters, 2 reps in the first year. Now we have planted out of those in the bigger trial, that is 6 meters squared and 3 reps. So results are, we are harvesting those material, we will get those results. I think these slides give you the idea that these in the first breeding cycle, when we have these 2,000 segregating population, and simultaneously in the greenhouse we also develop a recombinant timber line of the same crosses in order. Now we are performing the GWAS, which I will let you know in next few slides. So then once we have the GWAS results, if we want to confirm, so that we have already population is available for them. So these sales population will be used to confirm any association we receive from these material. So you can see how these wild type of, these are the segregation population. Then you can see how we will get more toward elite type when we go to F6 and F7. And then on the back, these are some of the heat trial we are planting this season in Oregon. So this is update status. As I mentioned that we have started in 2012. We have the pipeline till 2022 already, number breeding pipeline, which we started from F2, go on the drought and heat and diseases and agronomic practice and make the selections. So we already mobilized more than 1,000 exotics through pre-breeding efforts, and we have generated 15,000 pre-breeding F6 germplasm, but that is not a bridging germplasm. So we need to work what the breeder can use. Breeder don't want that much, they may plant 10, 20 or 30 lines. So but as we want to bring the variation, not sake of variation, we want to see the utility or the useful of this variation. That's what we need to strengthen the linkage across the expertise, so that we can reflect what are the needs, what are the necessities. So that is the way we are working on this program. So out of those 1,000, we have selected out of those first batch, we have selected 1,000 best lines, and those 1,000 lines already we have shared with the partners, national partners, and others who have requested the material. Some of you have visited the field at Obregon during the visitors week. They have requested the material, but most of the people need, we have 200 lines, we just need to handle 200 lines. They don't have the resources to handle a large number of material, but we have some partners in Pakistan, they have got the funding, and similarly in some institute in India, Punjab Agriculture University, they want 1,000 lines, and Paulov Institute also we have some funding coming from the government, which can handle some of those material. Then they can distribute based on the target region, what are the value for those regions. And they find these resources are useful not only for drought and heat, but other things. So you have seen the previous slide, very wildly typed. So when we move on, make the selection, we bring the material to reasonable, so that breeder like to use at least in their crossing block. We are not going to release this, but this is going to the breeders so that they can see how this is good fit for their programs. So now the next question is, okay, so we are doing all these efforts, how it is going to be useful? Then we have the GBS of all this material which we are generating by using the dart stick. So these are 1500 lines. If you look here, blue are the pre-breeding lines, reds are the elite, and greens are the exotics. So we can see in the circle, some of those lines are not close to either of the parents. So those are some of the, we know breeding creates the variation, but we have the data, we are showing that it's it's there. So okay, that's one thing, but what is next? So we have planted this material in the drought, heat and irrigated at Obregon. Then we have the GBS markers. So we performed the analysis and looked at this data set, and we found the QTL on chromosome 4A and 6D, and we know they are not effect of headings and flowering, they are stress responsive. Then go to the further, then we look these allele of responsible, and these alleles are coming from minor alleles out of 1000 lines. Only 40 lines have the allele. You can see here, I think this is PT and other one is CC, which is present in the elite line, but our dried material have this minor haplotype, and this is responsible for heat, under heat condition, give better performance. So then we took these elite lines and do the PCA analysis, and you can see these blue one here are the pre-breeding lines with the minor haplotype, and the others greens are exotics and elite are red line. So if you look genetically, they are in different, most of those minor allele lines are in different genetic space. But when we look in the field, they are very close to the elite. So this gives us that we have the scope to use this material to broaden the genetic base of our wheat, right? So then comes to, okay, we found this association, but next comes in, what is the contribution of exotic? Because I already mentioned that our alleles have a lot of good things. They have wide adaptability, disease resistance, and they also have tolerance to some of these stresses. So then we have to think, and one of our key player, Deepmala, is also here. So she has done quite a bit of work on to how to develop. Then we developed the haplotype map of all the exotics separate, all the chromosomes, elite, and pre-breeding lines. So we have three set of the haplotype map of this germplasm. Then you can see in this slide that we have black dots. Those are the exotic specific haplotype in those particular chromosomes. Whereas the other haplotype block, that is with the yellow spots, and we found that 22 haplotype blocks are associated with different traits, which I will explain in a minute. Because we distributed this material to the partners, that is the strength. They give us the data for different traits, they have evaluated for diseases and other things. So when we get those data now with the association, we found what are the exotic blocks are associated with the trait of particular interest. In this slide, this is an example here for 7A, 5A, 6B and 1D. These blue are the grain yield. The block here in the red square is the haplotype block specific to the exotics. So where you can see the blue, that block is associated with the grain yield, yellow one is associated with yellow rust, some are associated with powdery mildew and others, so and so forth. So most of the data is coming from the partners, and when that's what the breeder like to see, to utilize the material when we show the value that, okay, this is specifically coming from exotics, because these, when we are talking about the haplotype of exotics, that is missing in our elite material, but present in our breeding dermatology. So these are these are the haplotype, and these are some of the chromosomes where these haplotype is mapped. Then we have the location where the data has been obtained for foliar diseases, powdery mildew, yellow rust, and yield and biomass is taken at Obregon. So these slides show that chromosome 1A, we have a haplotype block 3 and 27 here. In block 3, we have two markers, number 45 and 46, which is in high LD 0.96, whereas in block 27 we have the three markers, 310 and 322 are also in high LD 0.89, but where we have seen in the dotted 30 marker 311 is not in very low LD with the marker 310 and 312. So that way we are trying to align these haplotypes. Similarly for 6B, we have also shown that with one of those of our studies we found this. Then I think I will move quickly as the time. So then some of the, I've already mentioned that we want to move this PBD plasma across the globe, and we already made some progress. We have last time in March in India, and we have very positive feedback from the NARS partner looking this material, and we already distributed to India, Pakistan, Iran, UK, US, China, and different peoples are using, but they have need to the resources to utilize these resources effectively in the future. So these are some of the pictures where the efforts is going on using this material, and this is the Mexican partners also using this material. So I think I'll go ahead, and then we are looking forward the linkage of this material to different wheat initiative and mobilizing like indeed RWs, Harvest Plus, IWGS or Hedwig and other sources, because these resources have a lot of investment from the Mexican government. We like to leverage how we can go to the next. At the end, I would like to thank you all.